So example 1 had us look at just the vertical asymptotes, but I know that there are other asymptotes there, and so example 2 is going to make us look at the horizontal asymptotes and see what adjustments we're going to make for those. So if you recall, to find the horizontal asymptotes, we need to look at the degree of the numerator and the degree of the denominator. The degree in the numerator we said was n for numerator, and in this case the degree of the numerator is 0. There's no x, so it's x to the power of 0. The degree of the denominator we said was m because it was m for denominator, which was a pretty lame joke. But in this case, the degree of the denominator is 1. And so we looked at it and said, if n is greater than m, that meant there was a horizontal asymptote at 0. Remember, our logic behind that is if the degree in the bottom is big on this fraction, that numbers keep going to get bigger on the bottom, and the top is going to be not as big. And the bigger you get, you end up getting a really, really tiny fraction that eventually it ends up being close to 0. So there's this horizontal asymptote at 0. When it's at 0, remember, we could actually plug in a big positive number and a big negative number, and you could actually tell if it was going to be above or below this by seeing if above was going to be positive, because above 0 is positive and below 0 is negative. So we could actually do it. We would have put in negative or positive infinity, but again, we're going to use our new notation, and we'll say we're going to investigate the limit as x approaches negative infinity of f at x, and the limit as x approaches positive infinity of f at x, and find out what happens when you put in a really, really big positive number or negative number. So when we put in negative infinity, of course, into the equation, in for x, the 3 doesn't care what x is. The 3 is going to be positive regardless. But when you put in a really, really big negative number, it's going to be negative on the bottom. And when you do this division, you'll end up with a negative small 0, or a negative 0. It's not really 0, it's just negative really close to 0, so I'm just going to put negative. But the negative tells you then it must be coming from below, because below 0 is negative and above 0 is positive. We can do a test point and putting in a really, really big positive number. Again, the 3 doesn't care. But when you put in positive infinity there, it's going to be plus, and that's going to tell me it's above 0. And so for this particular one, if I was looking at the horizontal asymptote, which is at 0, I can tell that on the left it's coming from below, and from the right it's coming from above. So this was great when the horizontal asymptote was at 0. But remember, when the asymptote's someplace else, this method doesn't help us. So if I had a graph like this, and I was looking at an asymptote that's up here, if I put in a really, really big number, it's going to be positive, because if this is, let's say, 3, and I put in a really, really big number, you might get something like 3.001. Well, guess what? That's positive. And if I put in a big number, I might get positive 2.999. The key is when you put in a big number, you'll get positive, and you can't tell if the graph is coming from above or below. It only works when it's at 0. And if I end up with a positive number, I actually know it's coming from above. And if I end up with a negative number, I know it's coming from below. So that method only works when you have a horizontal asymptote at y equals 0. If we didn't go any further. Well, now I can tell you, because we have this idea of the limit, I can tell you of a way to figure out if it's coming from above or below, even when the asymptote isn't at 0. So we'll do that in this example. So example 2b. In example 2b, I have the function 2x over 7 minus x, which I can think about it like that, or you might like to think about it as 2x over negative x plus 7. Means the same thing. So if I want to investigate the horizontal asymptote, I need to look at the degree of the top, which in this case is 1 because it's x to the power of 1. And the degree in the bottom is also 1. And so we have a situation where the degrees are the same. When the degrees are the same, we're going to look at the leading coefficients. Because the numbers are going to be essentially really, really big and close to each other, so the leading coefficient will be the only way to tell what the horizontal asymptote is. And in this case, the leading coefficient on the top is 2, and the leading coefficient on the bottom is negative 1. So therefore, the asymptote is going to be at y equals 2 over negative 1, or y equals negative 2 is the horizontal asymptote. So in a moment, we can think of this graph, and there'll be a horizontal asymptote down here at negative 2. But again, if I just put in negative or positive infinity, the answers are going to be negative because we're down at negative 2. And it won't tell me if it's coming from above or below. So I can just make a note of that. Both limits will be negative since the horizontal asymptote is at a negative number. So we need something else to be able to tell if it's above or below. So we need help. Oops. We need help. And that help is going to come in something called the Directrix. The Directrix is a new kind of function whose only purpose is to help you determine if a graph is coming above or below an asymptote. It helps us with the direction. We can find the limit of the Directrix, and if the limit of the Directrix behaves a certain way, then we know what the original function does. So now the question is, what is the Directrix and how do I find it? So the Directrix comes from actually doing the division that's involved in these rational functions. Remember, this division, this line here means division. So let's actually do the division. And we've done this before, so this is good news, but you'll see where it becomes helpful. So let's do the division here. In the top, you'll notice that it's 2x divided by x, or negative x plus 7. How is that written? 2x divided by negative x plus 7. This is why it's easier to have it in this notation, have the x first. So let's actually do the division. So to do the long division, remember I asked myself, what number gets multiplied by negative x to get 2x? And that number is negative 2. I'll have to put it above the 0 here. And I multiply, so negative 2 gets multiplied by this, and I get negative 2x minus 7 or 14. That's negative 2 times 7. Oh, sorry. negative 2 times negative x is going to be positive 2x. Sorry. But it will be negative 14. Now when I subtract, of course, these are going to disappear. But this will be 0 minus minus 14, which will be a plus 14. If you recall, the answer here is an asymptote. Well, guess what? We already knew that. We already knew what the asymptote was. We did this before to find oblique asymptotes, and we're going to do that again. But in this case, we actually care about the remainder now. The remainder is going to be an important part of our directrix. So our directrix is a new function that I'm going to call capital D, and it is the remainder over the denominator of the question. So in our example, the directrix is the remainder, which in this case is 14, over the original denominator. And if you look back up, the original denominator is right there, negative x plus 7. So as I said before, this directrix is a different function, but if I look at the limits on the directrix, it will tell me the direction of the graphs of the original functions. So now I'm going to use the same notations I did before. I'm going to take the limit as x approaches negative infinity, and the limit as x approaches positive infinity, but instead of doing it on the original function, I'm going to do it on the directrix. And the way the directrix behaves will tell me what the how the original function behaves. So, still, same idea. I put in a negative huge number. When I put it into this function here, into this, notice when I put in a number for x, the 14 isn't going to change. So it's still going to be positive. But if I put in a negative huge number right here, and then it's got a negative already, it's a negative of a negative, that's going to be a positive huge number. Plus 7 isn't going to have any influence on it. It's going to be positive, and the result will be a positive, which means it'll come from above my horizontal asymptote. Because if it comes above the directrix, it will come above our horizontal asymptote in the original. Put in a positive huge number, or yes, a positive huge number. Again, the 14 doesn't care. But if you put in a positive huge number into here, you're going to put a minus in front of it, so think of a billion. Put a minus in front of that's a negative billion. If you add 7, that's not going to really change it. It's still going to be negative. And the result will be a negative, which means it comes from below the horizontal asymptote. And so now I can actually go back to my original graph, my sketch up here, and know that I might as well just redraw it here so I can see everything. I knew already the horizontal asymptote was at negative 2, and now I know on the left-hand side, as it approaches negative infinity, it's coming from above, so it's going to do this. And from the right-hand side, it's going to come from below, so it goes like that. And this information I didn't have before when I didn't know the directrix.